Hello, myself Vinit from Chemistry Honors second year. Today our chapter is Electrochemistry for visually impaired students. So for electrochemical cells, 2Na plus Cl2 gives 2Na plus 2Cl minus. It occurs by the transfer of electrons from Na to Cl. Na loses an electron and is said to be oxidized to Na plus ion. At the same time, Cl gains an electron and is reduced to Cl minus ion. Such a reaction, which is brought about by loss of electron oxidation and gain of electron reduction simultaneously, is called an oxidation reduction reaction or redox reaction in brief. So, types of electrodes. First, metal ion electrodes. A metal rod that dipped in an electrolyte solution containing metal ions. There is a potential difference between these two phases, and this electrode can act as a cathode or anode. Anode पे reaction होगी, metal gives Mn plus Ne minus. The potential of a single electron in a half cell is called single electrode potential. So the Nernst equation takes the form E is equal to E naught minus RT divided by ZF ln A m raised to plus n. Second, gas electrode, standard hydrogen electrode SHE. Electrode gases like H2, Cl2, etc. are used with their respective ions. For example, H2 gas is used with a dilute solution of HCl, H plus ions. The metal should be inert so that it does not react with the acid. Anode, H2 gives 2H plus 2 electron. Cathode, 2H plus 2 electron gives H2. This electrode is also used to measure other potential EMF. Its own potential is estimate to 0 volts as reference. The concentration of HCl is 1 molar and the electrode is called standard hydrogen electrode SHE. The EMF of unknown half cell E naught can then be calculated from the expression E is equal to ER minus EL, where ER and EL are the reduction potential of the right hand and left hand electrodes respectively. The standard hydrogen half cell or standard hydrogen electrode is selected for coupling with the unknown half cell. The EMF of the standard hydrogen electrode is arbitrarily assigned the value of 0 volts. So, standard hydrogen electrode can be used as a standard for other electrodes. Example, it is desired to determine the EMF of zinc electrode Zn to Zn2 plus. It is connected with the hydrogen electrode and the EMF of the complete cell determined with a voltmeter. The EMF of the cell is the EMF of the half cell. E cell is equal to ER minus EL, that is minus 0.76 minus 0 gives minus 0.76 volts. Minus 0.76 volt is the EMF for Zn, that is zinc. Metal insoluble salt electrode. The standard hydrogen electrode is not the most convenient standard electrode to use in laboratory. The gas has to be carefully controlled. Metal insoluble salt electrode system whose potential has been determined relative to the SHE can also be used as a secondary standard electrode. Part A. The standard silver chloride electrode. In this electrode system, silver wire is covered with silver chloride, a highly insoluble substance. It is dipped in potassium chloride solution in which the concentration of Cl minus ion is 1 molar. This electrode cell can be represented as. The corresponding half reactions can be presented as Ag plus electron gives Ag. AgCl in solid form plus electron Ag solid plus Cl minus, or can be written together AgCl plus Ag plus electron gives Ag plus electron plus Cl minus plus Ag plus. which can be simplified as AgCl solid gives Ag plus plus Cl minus. The Nernst equation shows the dependence of the potential of the silver chloride electrode on the activity or effective concentration of chloride ions. E is equals to E naught minus RT by F ln ACl minus. The standard electrode potential E naught against standard hydrogen electrode SHE is 0.230 volt. The Coulomb electrode. It is the most commonly used secondary standard reference electrode. The standard Coulomb electrode SCE is represented as Cl minus 1 molar Hg2Cl2Hg, and the half cell reaction is Hg2Cl2 plus 2 electron gives 2Hg plus 2Cl minus. Glass electrode. A commonly used secondary standard electrode is the so-called glass electrode. Its EMF is determined by coupling with the standard Coulomb electrode. The glass electrode provides one of the easiest methods for measuring the pH of the given solution. A simple type of glass electrode consists of a glass tube having a thin walled bulb at the lower end. The bulb contains a 1 molar HCl solution. Sealed into the glass tube is a silver wire coated with silver chloride at its lower end. The lower end of the silver wire dips into the hydrochloric acid forming silver chloride electrode. The glass electrode represented as AgCl 1 molar HCl H plus. When placed in a solution, the potential of a glass electrode depends on the H plus ion concentration of the solution. The potential develops across the glass membrane as a result of concentration difference of H plus ions on the two sides of membrane. This happens much in the same way as the EMF of a concentration cell develops. The potential equation of a glass electrode can be determined as E is equal to E naught plus 2.303 RT divided by NF pH. Two electrochemical cells. A device for producing an electrical current from a chemical reaction, redox reaction, is called an electrochemical cell. Galvanic cells. A galvanic cell, also known as a volcanic cell, one in which electrical current is generated by spontaneous redox reaction. A simple volcanic cell is shown below. Here the spontaneous reaction of zinc metal with an aqueous solution of copper sulfate is used. Zn plus Cu2 plus gives Zn2 plus Cu. A bar of zinc metal anode is placed in zinc sulfate solution in the left container. A bar of copper cathode is immersed in copper sulfate solution in the right container. The zinc and copper electrodes are joined by copper wire. A salt bridge containing potassium sulfate solution interconnects the solution in the anode compartment and the cathode compartment. The oxidation half reaction occurs in the anode compartment. Zn gives Zn2 plus 2 electrons. The reduction half reaction takes place in the cathode compartment. Cu2 plus 2 electron gives Cu. When the cell is set up, electrons flow from zinc electrode through the wire to the copper cathode. As a result, zinc dissolves in the anode solution to form Zn2 plus ions. The Cu2 plus ions in the cathode half cell pick up electrons and are converted to Cu atoms on the cathode. At the same time, SO4 minus ions from the cathode half cell migrate to the anode half cell through the salt bridge. Likewise, Zn2 plus ions from the anode half cell move to the cathode half cell. This flow of ions from one half cell to other completes the electrical circuit, which ensures continuous supply of current. The cell will operate till either the zinc metal or copper ion is completely used up. Now moving towards the cell reaction. The flow of electrons from the one electrode to the other in an electrochemical cell is caused by half cell reactions taking place in the anode and cathode compartments. The net chemical change obtained by adding the two halves reaction is called the cell reaction. For a simple volcanic cell described above, we have half reactions. Zn solid gives Zn2 plus aqueous plus 2 electrode at anode. And if we talk about cathode, then Cu2 plus aqueous plus 2 electrons gives Cu solid. Cell reaction, cell over all reaction. By adding up the half reactions, Zn solid plus Cu2 plus aqueous gives Zn2 plus aqueous plus Cu solid. Cell diagram or representation of a cell. In 1953, IUPAC recommended the following conventions for writing cell diagrams. We will illustrate these with reference to zinc copper cell. A single vertical line represents a phase boundary between metal electrodes and ion solution electrolyte. Double vertical line represents salt bridge, porous partition or any other means of permitting ion flow while preventing the electrolyte from mixing. Anode half cell is written on the left and cathode half cell on the right. In the complete cell diagram, the two half cells are separated by a double vertical line salt bridge in between. The zinc copper cell can now be written as Zn2 plus double vertical lines Cu2 plus single vertical line Cu. Calculating the EMF, electromotive force of a cell. The EMF of a cell can be calculated from the half cell potentials of the two cells, anode and cathode, by using the following formula. E cell is equal to E cathode minus E anode. ER minus EL, right minus left. Let us predict the EMF of the cell. Zn solid gives Zn2 plus aqueous. Ag plus aqueous gives Ag. By using the E naught values from the table, E naught cell, E naught right minus E naught left, 0.80 minus 0.763. So it will give us 0.80 plus 0.763 and it will give us 1.563 volt. The answer is so clear that the E naught cell is 1.563 volts. Electrolytic cell. Electrolysis. What is electrolysis? The decomposition of some substance by means of an electric current is called electrolysis. What are electrolytic cells? A cell that requires electrical energy to cause non-spontaneous oxidation reduction reactions to occur. It utilizes an external source of electric current. It forces electrons to flow in the opposite direction by applying a voltage greater than the cell potential. It converts electrical energy into chemical energy. A salt bridge can be used in electrolytic cell or not used. Difference between volcanic cell and electrolytic cell. Volcanic cell, spontaneous redox reaction. Electrolytic cell, non-spontaneous redox reaction. In case of volcanic cell, reaction releases energy. Electrolytic cell reaction absorbs energy to drive it. Electrolysis of water is the decomposition of water into oxygen and hydrogen gas due to the passage of an electric current. This technique can be used to make hydrogen gas a main component of hydrogen fuel and breathable oxygen gas. The base balanced reactions predominate in basic high pH solutions. Cathode reduction. 2H2O liquid plus 2 electron gives H2 gas plus 2OH minus in aqueous form. Anode oxidation होगा. 2OH minus aqueous form gives half O2 gas plus H2O liquid plus 2 electron. Combining either half reactions pair yield the overall decomposition of water into oxygen and hydrogen. Overall reaction. 2H2O liquid gives 2H2 gas plus O2 gas. The number of hydrogen molecules produced thus twice the number of oxygen molecules. So this was our chapter. So thank you very much.